First of all, good afternoon, everybody. Again, thank you for joining us here in the DeFord lecture series. And as I mentioned before, if during the course of the talk you have any questions, please just type those into the question and answer box. This is part of the fall 2021 DeFord lecture series. The DeFord lecture series used to be called Technical Sessions. Is a long-standing tradition amongst the faculty and graduate students in the Department of Geological Sciences in the Jackson School. It was started back in the late 1940s as a way for students and researchers to disseminate their research results to the community. And it's been named after Ronald Kinnison DeFord, who joined the university as a professor back in 1948. And was a graduate advisor in the department from 1949 to 67. He supervised a phenomenal 19 PhD dissertations and 126 master's theses, and was very active in the department. And one of his enduring contributions was his leadership in the graduate course that at that time was called Technical Sessions. And so it had subsequently been renamed in his honor, the DeFord Lecture Series. We are virtual this fall, and as was announced in the faculty meeting just the other day, we have now made the determination that the spring DeFord series will also remain virtual. We all hope that at some point we can go back to inviting illustrious speakers like Dr. Barnes to actually join us here in Texas and show our Texas hospitality and some of the best taco places in town. But for the time being, we are remaining virtual, which has the benefit that people from around the world can join us both as speakers and as visitors, listen to these lectures. And so with that rather long-winded introduction, I'm very happy to hand off to Dr. Persad, who will be introducing today's speaker.
Thank you, John. And we will have to arrange to send at least a bottle of queso to Dr. Barnes to show some Texas hospitality. It's my real pleasure to welcome Dr. Elizabeth or Libby Barnes as the second DeFord lecturer of our fall seminar series. On behalf of myself and the many other Jackson School faculty who actually nominated Dr. Barnes for this lectureship. Dr. Barnes is an associate professor in the Department of Atmospheric Sciences at Colorado State University, where her research group has been really pioneering the use of data science to understand fundamental questions in climate variability and climate change. And I've been particularly inspired by her group's approach to thinking about data science and data analysis design as a core part of studying the Earth system rather than as an afterthought. And I think you'll see some of the real benefits of that in her talk today. Her creativity in these approaches has helped her group make major advances in topics ranging from detecting the global human footprint and satellite imagery to revealing causal pathways of the Madden-Julian oscillation, which has been a real stumbling block for subseasonal weather prediction, just to name a few of her recent research projects. Dr. Barnes holds a bachelor's in mathematics and in physics from the University of Minnesota and a PhD in atmospheric science from the University of Washington, and has received multiple awards for her teaching and research, including an NSF Career Award in 2018 and the AGU Future Horizons in Climate Science Turco Lectureship Award in 2020, which was one of the best Turco lectures I've seen in a long time. Today, she's going to be discussing how viewing anthropogenic change through the lens of artificial intelligence can help us uncover new insights. So welcome, Dr. Barnes.
Thank you for that intro. Wow, that was great. Okay, now you know a little bit about me. Let me tell you about some of our work here. So thank you so much for this invitation. I always love it when people are willing to get together and nerd out with me about using data science tools, in this case, machine learning, to explore our Earth and what we are doing to it. So just to get started here, before I get into the meat, I want to acknowledge that this is truly a group effort. I have many collaborators across the world, but my main collaborators here are my students and postdocs shown here. This is our most recent quote group photo. And I just want to acknowledge that many of them are doing the awesome work that I get to talk about today. And I will get to touch on a few of their work, but I will comment on a few others. All right, so as geoscientists, I like to start off with just saying we have a big toolbox already. We have fundamental theory, we have spectral analysis, maybe correlations. We like to take regression, do regression. Some of you PCA, so principal component analysis, or EOF analysis is something many of us know in the climate sciences and use a lot. We have things like just drawing a trend line through a bunch of data. That tells us something, right? It's going up, the climate's warming, for example. And then finally, maybe our most advanced tool in geoscience, and especially in climate science, is our dynamical models, our Earth system models that are attempting to simulate so many different parts of the Earth system. All of these tools are useful. They're certainly in my toolbox, and I use most of them, many of them, you know, every week. I want to suggest that machine learning is really just an additional tool. Maybe it's the screwdriver for our already exploding toolbox. It's not the right tool for all of the jobs, but one of the fun things I've been doing the last few years is trying to ask, when is it the right tool, and how can we get creative in how we use this tool to do things maybe we couldn't do before with what we've already been doing in the past. So the way I think about it is that one of our jobs as scientists, one of them, is to sift through piles of data, some mountain of numbers, and extract useful relationships that apply elsewhere. Computer science lingo, this would be, you know, find relationships that apply out of sample. But really, as scientists, we might just say find the physics and that, you know, the relationships and that connect the Earth system to different pieces. And so this is really what many machine learning methods are designed to do: sift through lots of data and find relationships. So what does that have to do with, you know, with climate science? Well, first of all, I'll step back and say machine learning is exploding in terms of interest everywhere, especially in the private sector. And so while I'm here to talk about machine learning in my work with climate science, I will point out that there are lots of commercial applications. Here's an interesting one that came out of NVIDIA a few years ago. You can find it on YouTube, where they take an image, say in this case of a woman, and they zero out her eye. Here, they just white it out. It looks sort of like in paint or something. And then they task a network to fill in the missing pieces. So this is interesting. I'm not sure why they need this, but it's cool. Okay, it works. But what a colleague did is they saw this and thought, this looks a lot like infilling temperature or temperature reconstruction from the past, and use this exact same model from NVIDIA, collaborating with them to actually try and reconstruct temperatures. Now, we have many methods in climate for reconstructing temperatures, that is filling in missing data, say in this case from 1877, but they used this particular machine learning technique to do it, and ended up having interesting insights about the 1877 El Nino. So I love this application. It's so neat. And one of the things I love about it is it shows how taking things from the commercial sector, as geoscientists, we can tweak them in our own way and make them our own and help us do science with them. So this is just one fun example, one of my favorites, but there are many other examples in geoscience and climate science in particular of using machine learning in recent years. For example, in the talk here, it's taking the idea of finding or identifying cats and dogs and taking that and turning it into pattern classification of extreme weather events like hurricanes or atmospheric rivers. Another one of my favorites is actually using machine learning to do equation discovery. That is, Zana and Bolton here in 2020 actually used machine learning to find different parts of a tensor and fill it in with the different terms that may be important. So in this way, we can use machine learning to actually understand the physics as well. I'll talk a bit about that today. It's being used in climate models for convective parameterizations. That's a big area being explored. For weather prediction, let's say a purely machine learning weather prediction model, how does that do against our current weather prediction models? Turns out it does okay. A purely weather prediction or machine learning model, but again, this is the beginning. So how can we improve it? And finally, machine learning is also just being used for climate change communication. So on the bottom here is a picture on the left of somebody's neighborhood, and they're using machine learning to try and fill in what this neighborhood might look like under sea level rise or inundation. So lots of different ways that machine learning is already being used in our field. So before I start jumping into research, it's helpful potentially if you're like me about 5 or 6 years ago saying, I've heard this term machine learning, and specifically in my group, we use neural networks, but what exactly is a neural network? So I thought I would take a few slides just to give a sort of the 101 of neural networks. So if you think about a neural network, we think about a neural network this way, the simplest one, you have some inputs, say they're X1 and X2, you can call them predictors as well. So something you think is going to help you predict something else. So what they do is they connect, and this is how we actually draw these pictures, this neural network architecture, this is how we draw it. You connect these different input nodes or units with this gray node shown in the middle here. And each of those arrows is associated with a weight, or a W1 and a W2, just telling you how much that X1 is contributing to this gray node. And then you see the summation sign. This just tells you to take X1 times W1 plus X2 times W2 and add them up. And then we also add a B or a Y-intercept. It's called a bias term, but it helps us shift everything up and down. But otherwise, up until now, we've just done multilinear regression, nothing too fancy. So what happens next is where the nonlinear part of neural networks comes in. We push this output through a nonlinear function called an activation function. And then what is output ends up being a value that was just this nonlinear mapping of this linear regression problem. So in essence, it's so far doesn't seem all that complicated. The whole idea, by the way, of training a neural network is finding the right W's, the weights, and the right B's, the shifts, to get out the number that you want, the thing you're trying to predict. Now, this doesn't look complicated, but you can imagine now stringing all these together. So the output of one of these gray units becomes an input associated with another weight to another unit. And as these connect or fully connect to each other, it gets pretty complicated pretty quickly. But ultimately, in the end, you want to output, say, some predictions, some values. Now, the complexity and nonlinearities of the neural network allow it to learn many different pathways of predictable behavior. And then the idea is, once trained, you just have this matrix of weights and biases, these W's and these B's, that allow you to take some new input and make a new prediction, maybe on data it's never seen before. So why might we use machine learning for science? One argument is to do it better. So convective parameterizations in our climate models are not perfect. We know this, we struggle with them, and maybe machine learning can help make them more accurate. Another is to do it faster or cheaper. A good example of this is radiation coded models is very slow, but very good. Maybe we can use machine learning methods to keep how good it is, but speed it up. And finally, maybe something that isn't talked as much about, but I'm hoping I can change that with you guys at least, is that we can use it to learn something new. That is, we can go looking for these nonlinear relationships maybe we didn't know were there. And I will say, I think this is maybe obviously very relevant for research, but more importantly, it may be slower and it may actually be worse, but we can still learn something. There's something to be said about sort of this fundamental understanding in this scenario. So today, I'm going to go through a few different examples of how we can use these methods. The first, I'll go through three, but the first one is going to be about doing it faster or cheaper. And the second one will be, and the third are going to be associated with learning something new. All right, so the driving question here, and sort of the title of my talks, is humans are changing the Earth in profound ways, but how does this differ around the planet, and how has it changed over time? So you can imagine this question encompasses so many different fields and subfields in geoscience. So my first example is detecting the human footprint on the land surface. So that is looking down on the Earth and trying to detect where humans have made an imprint. All right, so why do we need a metric of the human pressures on the landscape? Maybe it's obvious, but there are actually a lot of applications and people are using this type of data already right now. So mapping the effects of human pressure is a big deal. It's hard work. Current efforts, there are many efforts that are ongoing to create such a metric, and they typically lag present day by at least 5 years because they are so intensive to make. They take a lot of data in lots of different ways to try and do this analysis. Now, the problem, of course, with this lag is that as humans, we are making changes to the land surface much faster than every 5 years. And this can matter on what we do can matter on year by year. Some changes may be reversible, And ultimately, some up-to-date metrics could be helpful and complementary for tracking global change. So as I mentioned, there are already metrics for doing this out there. So Williams et al. 2020 has their updated, what they call the Human Footprint Index. This is a map of that index for the year 2000. So the dark purple is like a 0, means humans really haven't impacted that region. And a bright yellow means humans are really impacting. You can think of it as sort of a shopping mall with pavement everywhere. So the way they come up with this index is they homogenize a bunch of data from built environments, population density, croplands, pasture roads, navigable waterways. They put this all together and come up with this one index. It's an amazing data set. And the biodiversity community uses this actually extensively. So our idea was, this is awesome, this is great. Can we train a neural network? In this case, it's a convolutional neural network that's a bit different than what I explained, but the general principle is similar. Can we train it to ingest Landsat imagery? So we take some pictures from Landsat of what the land looks like alone from, say, the year 2000, where we have data, and we input it into our CNN. And in this case, I will say this Landsat imagery already exists, all cleaned up and ready to use if you're interested. And so they have data from, again, the year 2000, and as I'll show, 2019. So we have this data, we want to input it into the neural network and output some prediction for that location of the human footprint, say some value from 0 to 1, where again, 1 is a large human footprint. So we did it, and this is obviously, there was a lot involved in doing it, and I'm happy to talk about it during question and answers, but it worked. And ultimately, we were able to make a similar map. Here's our, what we call MLHFI for machine learning human footprint index. And you can't really tell, but in the paper we'll convince you hopefully that this is quite similar to the original human footprint index shown in the bottom left here. So this was again used, created and computed from Landsat imagery alone. Now you might say, what was the point of doing this? We already had a human footprint index by Williams et al. The idea is, now that we have this neural network that can take in Landsat imagery and produce this number of the human footprint, we can use Landsat imagery from other years and create a different data set for that year's human footprint index. And in fact, what we did was we took that 2019 Landsat imagery and we're able to create an up-to-date human footprint index map. Now, if I flip back and forth, I'm not sure if you can see, but some regions brighten, and that's really where humans have had an even bigger impact than they did in the year 2000. So big changes over the last 20 years. So this is fun, and we can do it, and people are doing science with this data set, cool. But I'm here to talk about what we do, I guess, and this is, the question that we ask next as scientists is, the picture's pretty, but are these predictions any good? How can we check we have the right answers for the right reasons? Because a human did not homogenize this data, our machine learning algorithm did. So how do we know that it's getting those right answers for the right reasons? So this often is called opening the black box. It's a phrase you'll hear over and over. And there are now many papers in our field alone that think about opening the black box for atmospheric and climate science. This is just a few examples of them. Now, there are many tools out there explored, for example, in these papers, and a large number in the computer science literature. Today, I'm going to talk about the particular tool that my group has found intuitive and useful. It is not, I want to be clear though, I'm not trying to say this is the only tool, and it's certainly not a perfect tool, but we found it useful for our science questions. That tool is called layer-wise relevance propagation, sort of a mouthful, so we say LRP instead. And the idea of LRP is it helps us look back into our network and understand how it came to the prediction that it did. So here's how it works. I want to be clear though, we did not develop this. This came out of the computer science community. So here's how LRP works. Let's say we've trained a network to predict if there's a cat in an image. So we put an image in and we've already trained our network. So now we want to know, is there a cat in this image? Let's say the network comes back and says, yes, there's a cat with a probability of 0.8. You say, okay, how did you come up with that? Where did that number come from? Well, what LRP does is it's an algorithm that helps you go back through the network that propagates that prediction backwards through the network to create a heat map showing you where in the input image was most relevant for the network's correct prediction. In this case, the heat map shows us that the network focused its attention mostly where there was a cat to determine there was a cat. This is not terribly interesting. We sort of probably expected that, but I'll hopefully show you that this can be useful for science as well. All right, so one way we use LRP for explainable AI, which is another name for these tools to help us open the black box, is again to ensure the right answers for the right reasons. And then before we return to our human footprint example, I wanna give you a fun little example of how this works. So here are two images, and they have horses in them. I hope you agree. And we've trained has trained a neural network to predict if there's a horse in the image. So the network gets it right. And then the question is, where did the network look to know there was a horse in this image? And if we make these LRP heat maps, you have to squint and for now ignore the blue, but you can hopefully convince yourself that the red regions generally line up with where there is a horse. And that's where the network thought was most relevant for its prediction. So far, so good. This is a lot like the cat example. Okay, how about these three images? Again, there's a horse in every image, and the network also correctly guessed there was a horse in every image, but where did the network look to determine there was a horse in the image? So you can make these LRP heat maps again, and you quickly see that the brightest regions, those yellow regions, are not where the horse is, but they're actually in the bottom left-hand corner. And if you look back at the image, you'll see that that's where the copyright symbol is. So this network has learned that whenever it sees this particular copyright symbol, there's probably a horse in the image, and so it should just guess horse. This is, as a scientist, this is concerning, of course, because we want it to get the right answer because there's a horse, not the copyright symbol. Since if I go out and take a picture of a horse and I push it through this network, it will say there's no horse there because it doesn't have the copyright symbol. So this is concerning. So these explainable AI tools, or this LRP method specifically, can help us find or ensure that our network is getting the right answers for the right reasons. So let's return now to this human footprint index problem. We were able to use LRP with our machine learning human footprint index to look at the network's approach for this problem. So what you see for each of these 6 examples, on the far left is the year 2000 Landsat imagery, in the middle is the year 2019 Landsat imagery, and on the right is the heat map for LRP, showing you where the network looked for its 2019 prediction. And you can see here that generally it's starting to pick up the man-made or the human-made features in these images, suggesting that our network is updating its human footprint index value for the right reasons. These are just some quick snapshots. So reasons to care about opening the black box or explainable AI or XAI. The first is helping you identify problematic strategies, like we showed with the horse. Another is building trust, similar to number 1, but helping us see that, yes, indeed, it's getting these right answers for the right reasons, and we might trust that output. A third is helping you choose the machine learning approach. So returning again to our human footprint example, the Landsat has many channels, and we didn't know which channel or which set of channels would be most useful for our problem. So in this example, I input 3 different channels to the network to make its predictions. And then I used LRP to help me, or these heat maps to help me determine which channel was most important for the network when it was making its prediction. And in this example, it shows that channel 3 was by far more important than the other 2 channels in getting the right answer, or in terms of its relevance. And because of that, we were able to shift which data we used as input and save on memory and storage space. So these are all 3 reasons why we really need to care about explaining our AI to do science with machine learning. However, there's a 4th reason, and that is to learn something new. And I mentioned that the idea that we can use these networks to learn something about the system we didn't know before. So imagine I have my data going into some black machine learning box here, and I make a prediction. It could be that instead of caring about the prediction, what we actually care about is how the network learned to make the prediction in the first place. If we can explain that, maybe we can learn something new about our system. So in my next 2 examples, I want to talk through in detail how we go through this process. So the second example is, again, thinking about anthropogenic change, but now we're thinking about indicator patterns of force change, specifically trying to find detectable patterns in our climate system of human-induced climate change. So when we think about the force change or climate change, we often just think about temperature trends. You know, it's getting hotter in lots of places. So on the left here are temperature trends over the early 20th century, and on the right, the end. And we see the globe is really, is warming here. Now, when you stop and you think about detecting climate change, there are a few things you have to think about. The first is the pattern of the change. What are these patterns, and which geophysical variables, precip, precipitation, temperature, etc., do these patterns relate to? The next is the timing of this detection. When can we detect? When can we see these patterns amidst all of the climate noise and in the physics of the climate system that's always there, this internal variability? And finally, we have a lot of climate models, and they all do things a little bit differently. Do climate models simulate these changes correctly? And do they simulate these changes similarly to each other, or how are they different? There's a lot of different questions we can ask when we really talk about detecting force change. So let me tell you how we're approaching this problem. And this is an example of where we've set up the problem where we don't actually care about the prediction, but we care about how the network made the prediction. Specifically, what we're going to do is we're going to take maps of annual mean temperature from many different climate models from the years like 1900 to 2100. We have lots of these annual mean maps. So if you want to, you can think of the year you were born. There's a climate model that has an annual mean temperature map for that year in its simulation. And what we're going to do is we're going to train the network to predict what year that map is from. Now, in this case, on the right-hand side, it's split into decades, and I can go into details. We're actually doing something called fuzzy classification. Mentally, you can just think of it as the network is predicting the year of the map. Now, we can stop and think like, why, what is the point of this? And ultimately, what's happening is in order for the network to be able to figure out the year, it has to be able to find the forced anthropogenic change. For example, know that 2020 is much hotter than 1920 and figure that out. Now, the internal variability, whether it's an El Nino year or a La Nina year in these climate models, is all mixed up. This internal variability is really noise. And so the network has to learn to ignore that and find and learn regional signals that are reliable indicators of the year. And it turns out these end up being that forced response to climate change. Okay, so we did this. We had lots of data from lots of different climate models. Turned out the network did a good job. So what does that mean? Well, we can make a plot of the actual year on the x-axis of the map that we fed it. And on the y-axis is the predicted year of the map that we fed it. And a perfect prediction would fall along this black one-to-one line. Now you'll see at first, the dots, the colored dots, by the way, are the testing climate models that the network has never seen before. And you see, especially as you get out into the 21st century, the network starts to do a very good job of predicting what year it is. Now, on the other hand, on the far left-hand side, you see it does a terrible job. It has no idea what year it is. It just sort of guesses generally about 1950 all of the time. And this is not, if you will, a failure of the network. This is actually the a climate problem. This is the idea that the forced anthropogenic climate change piece is so weak and small compared to the noise of the climate system and uncertainties in our climate models that the network is unable to find a reliable indicator of the year. And it isn't until about 1970 or so that the network starts to be able to find patterns where it goes, I know what year it is. That is, it starts to find these patterns of forced change. Now, I will note, all of this was done thus far with climate models. And you might say, well, what about the observations? Well, one of the neat things is once we've trained this network, we can push through any map of temperature that we want. In this case, we push through observed annual mean temperature maps. And we ask the network, what year do you think it is? And in this case, the white dots show the predicted year based on observations. What we see is that the network does a generally pretty good job at predicting the year from observations. And what this means is that the neural network has learned useful relationships from the climate models that apply to the real world, which is pretty cool. All right, so I could pause here and say, look what we've done. And you might stop and go, wait a second, you just predicted the year of a map. Nobody really cares what the year of a map is, right? Like, we know what year it is. We know it's 2021. We don't need a neural network to tell us this. No one's going to pay me the big bucks to be able to predict what year it is. So, predicting the year does seem pretty silly, and it really is. But with explainable AI tools, or LRP, for example, we can ask the question, what if we could learn which regions of the globe were most relevant to predicting the year? That is, where are these patterns of change showing up that the network is picking up on? So that is, we are going to identify these indicator patterns of climate change, these regional indicators that the climate is changing due to anthropogenic change, using explainable AI methods. Specifically, we have our network, it's made a prediction. Now we're going to use LRP to go backwards through it and ask which regions are relevant for correctly predicting the year. And when we do this, we get a heat map on the globe that might look something like this. That is, this is the heat map for the year 2015, or the most relevant regions for the network when it got 2015 correct. So we see, for example, a signal over Southeast Asia, one over the North Atlantic, and another big signal over the Southern Ocean as important regions for the network's correct prediction. Now we can do this for more than just the year 2015. We can do this for any of the years we analyzed. And here are just some examples. So 2015 is in the upper left, but 2095 is in the bottom right. And because the network is allowed to be nonlinear and learn different pathways, we can actually get different indicator patterns for the different years. Now, a few things to point out that we found interesting. One, we think this might be an aerosol signal, an anthropogenic aerosol signal around the turn of the century that the network has picked up on as being an important indicator that it's around 2000, 2015 or so. Another is this is a terrible projection, but you might sort of notice that there's really no Arctic signal. It's actually quite white up there. What that means is the network is not placing a lot of relevance on the Arctic. And if you study climate change, or you've looked at maps recently of warming over the globe, you might say, well, hold on, the Arctic's really hot and it's getting even hotter. That is, it's actually getting hotter faster than the rest of the globe. Why is the network using this as an important region? And the reason is the network's actually doing exactly what it's supposed to. It's supposed to find reliable indicators of the forced change. And what it is while the signal in the Arctic, that is the temperature change, is very large, the internal climate noise over the Arctic is also very large. And climate models tend to disagree on the timing of Arctic warming and change. Putting all this together, the neural network has decided that the Arctic is not a reliable place to look, and it will look elsewhere when it predicts the year. All right, so this is all done with temperature, and you may be thinking or wondering, what about precipitation? And we do show that in our paper. But another thing that we found interesting in the last year is, well, one of the things that's great about neural networks is they can ingest a lot of different types of data all at once to do this prediction problem. So my master's student, Jamin Rader, is starting to ask, what if we input temperature and precipitation maps and the different seasons? I see quickly there's a question up here about seasons, but the different seasons of those different variables into the network altogether. Can we do a better job at identifying change? For example, we know that precipitation in terms of the rainy season and the dry season may respond differently and have different detection times with warming. So Jamin, once again, has set up a network to predict the year, given now 8 maps, 4 of which were temperature and 4 of which are precipitation, all from a given year. And then once the network successfully does that, he is able to go back through the network with LRP and ask which regions of the globe were most relevant for your prediction. One of the fun things he's done then is he can actually make these LRP heat maps again. This one's for precipitation, so June, July, August precipitation, and make a plot showing these are the regions where precipitation provides unique information beyond what the temperature patterns would do alone, since temperature is clearly a very important indicator of climate change. And so he finds these specific regions, specifically, the sort of equatorial Africa here and sort of over India, and parts of China as being exceptionally important in the network's prediction above what it got from temperature. And I will point out, for those of you that think about detection of climate change, you might wonder what the signal to noise map looks like. And this is just a standard signal to noise map of this same field, showing you that the signal to noise is calculated grid point by grid point, whereas our relevance from our neural network incorporates data and information from all across the globe in determining these indicator patterns. So they don't look the same, although they share some features. Okay, great. So that is how we're using, this is one way we're using explainable AI methods to start to understand these reliable indicator patterns of climate change. And also, if you will, take a lot of information about signal to noise, climate model agreement, the forced response to climate change, different parameterizations within different climate models, put that all together to try and ask the question, where should we look to detect change? I don't have the slides here just to make sure the talk stayed within time, but if you're interested at the end, I can talk about how we can use this similar approach for the observations and ask about indicator patterns within observations themselves. All right, so that's one way we're using XAI to answer questions about detecting force change. But another part of that, as I mentioned, is internal variability. The fact that the climate system is noisy, and we know that there's going to be ups and downs in temperature, regardless of even a human impact. So in this final example, I want to talk about detecting mechanisms that are driving global temperatures. In this case, a PhD student, Emily Gordon, is thinking about decadal variability within the climate system and understanding those mechanisms so that we can also understand recent trends. So specifically, she has been looking at sort of an ocean phenomenon known as the Pacific Decadal Oscillation. It's the slowly varying pattern of ocean heat content and sea surface temperatures over the Pacific here. So it's associated with temperature and precipitation predictability over North America. It's linked to the Indian monsoon, ecosystems and fisheries, et cetera, on these decadal timescales. And so the pattern is shown there. And you can see from the time series below that sometimes it goes up, sometimes it goes down. And it turns out that these low frequency fluctuations can absolutely impact global mean temperatures, upon which the forced response is there as well. So what is Emily doing? Well, what she's trying to do is predict when this PDO index, when this climate pattern goes up and down, that is when it transitions from one phase to the other. Specifically, what she's doing is she is inputting 3 maps of ocean heat content from the past. So today, a few months ago, and a few more months ago, she's inputting these into a neural network to ask, in the next 30 months, will the PDO transition, that means flip sign and change its phase, or will it stay persistent and stay in the same phase? As an example here, here's the PDO, and you can imagine inputting the past 3 maps and asking over the next 30 months, will my index cross the 0 line or not? In this case, if you can sort of squint within that orange circle, you see that the dotted PDO index crosses the 0 line. So a correct prediction here would be a transition. Now, this on its own actually would be really helpful if we were able to predict transitions and persistence of this low frequency mode of climate variability. But on top of that, she wants to use it to understand where the mechanisms driving this behavior is coming from, so we can better understand it as it lays on top of the forced response. That is, she wants to first train the model and then again use this layer-wise relevance propagation method to go back through the network to understand which regions of the globe are most important for predicting this persistence. I will note, it's not written here, as a proof of concept first, she's been exploring this with climate model data. Why? Because we have a lot more climate model output than we do observations. And the first step is to see if such an approach works and makes sense. Okay, so what are the results? Well, she ends up with some heat maps, like always, of where the network looks to make its correct prediction, in this case of a transition. On the left-hand side is the transition from a positive to a negative phase. And on the right-hand side is a transition from a negative to a positive phase. It turns out that the neural network is looking at ocean heat content anomalies in the off-equatorial Western tropical Pacific. You can sort of see the red, hopefully, within that pink box. And the neat thing is there are theories for how this occurs, and this mechanism actually does agree with current theory. So far, so good. We think our network might be learning the right things for the right reasons. Interestingly, the right-hand side doesn't really have that anomaly in the pink box, if the pink box are there. Instead, it's really focused on the North Atlantic for predicting what's going to happen in the coming years over the Pacific. And it turns out that the North Atlantic is really important in driving El Nino, and this is an important piece of driving these Pacific decadal oscillation transitions. That is, the network, because it's allowed to be nonlinear, has recognized distinct transition mechanisms depending on whether the PDO is going from one phase to the other or vice versa. In this way, LRP, again, paired with this nonlinear method, is allowing us to explore these transitions and the mechanisms behind them in new ways. Now, I will point out, someone might ask the question, well, hold on, you didn't show causality here, and you're just, making some guesses at the mechanism. And that's absolutely correct. We sort of see this as a first step, or I think I mentioned in a meeting earlier today, hypothesis generation, where now we can go into climate models and continue and run experiments to continue to try to understand these two distinct mechanisms between the two different transition types. Okay, so to end my talk, I want to talk a little bit more about future direction. So zoom out a bit. I've given you a lot of discussion about some specific projects that my group is working on, but give you a bit of a broader picture. First, I want to point out, before I leave my group, I said I would show you a bunch more faces here. I want to point out that we're finding this use of explainable AI paired with these nonlinear function estimators, machine learning, is really helpful, both in some questions with subseasonal to decadal predictability. I showed you Emily's work with decadal prediction, but we're doing similar types of questions on much shorter timescales associated, as Gita said, with the Madden-Julian oscillation. We're thinking about the forced response of mid-latitude dynamics to different changes, for example, sea ice loss or tropospheric heating from climate change. I talked about the indicator patterns work done by Jamin. And then finally, we are also actually trying to do new science in these explainable AI methods themselves that has come up with new ways to benchmark which methods, which explainability methods are better for different applications, and also how can we design our networks to make more robust predictions and incorporate uncertainty in a way that is applicable and useful for geoscientists. With that said, this is what my group's doing, but I think there are some, if we zoom out even further, there are some bigger ways I think that machine learning is going to make really exciting inroads in the field of geoscience, and maybe more specifically climate science. And the first is knowledge-guided machine learning. So if you're a scientist who hasn't had much experience with machine learning, you might have this feeling of, wait a second, why are we throwing out hundreds of years of physics just because this machine learning thing came along? And then I agree with you. Things like F equals MA seems like a pretty good equation. Why are we throwing it out just to learn from the data alone? And so there is a bunch of work coming out now from computer science, as well as the geoscientists themselves, exploring how we can fuse scientific knowledge and AI together to sort of get the best of both worlds. And there's a lot of reasons to do this. And one of them is the high complexity of the Earth system and the fact that observations wise, we just don't have that much data. We have a good amount, but machine learning is data hungry. So how can we use the physical knowledge we already have to augment that data to help the machine learning algorithm find useful and important relationships? Another use of machine learning with observations that I think is going to be big moving forward is, I've shown you some examples where we use climate model data and we train our network. But what if the climate models aren't perfect? What we really want is we want to train the network on observations, but we don't have enough observations to do this. So the concept of transfer learning is that we first train a machine learning model with climate model simulations alone, and then we update this model or tweak it a little bit with data from observations. That is, we can leverage, again, the vast amounts of climate data we have, but acknowledge that the climate models are imperfect and we need to update these prediction systems with the observations that we have. The hope, and sometimes the result, is that a trained prediction model leverages these dynamical simulations, but applies better to the real world, which is typically the ultimate goal. And there's a nice paper by Ham et al. Now 2 years ago showing that transfer learning, training on climate models, and then updating that model with observations helped improve ENSO forecasts at about 6 to 12 month lead times. And finally, again, with climate projections, or you can think of these as just our dynamical models for the Earth system, how can we bring machine learning methods in to the building and the evaluation of climate model projections? So my work really has been in the evaluation, the analysis of these climate models, but how can we actually use them to actually simulate the Earth system in new ways? And I already mentioned convective parameterizations is one way people are using machine learning to try and make our climate models better. And on top of that, how can we potentially bias correct them with these statistical methods? All right, so my final slide here, some final thoughts. So I think the field of geoscience, I really do think we're poised and ready to leverage these tools. We use a lot of tools already from data science and statistics, and I think these are just another tool for the toolbox. They're not black boxes, and by visualizing their decisions, I do think now we can ask why rather than just make a prediction. We don't have to just make a forecast. We actually can understand why that forecast was successful and what physical processes led to that predictability. I will say, I think as geoscientists, we want methods that fit the way we do science, and a lot of these methods coming from computer science were developed for computer science problems, and that there is a place, there is a role for our domain science to develop these methods that are tailored to our needs. And finally, this is the part, I always leave it for last, but it's the reason I'm having fun, is that I do feel a bit like I can get creative. There's so many new ways that we haven't thought of that we can, I think, use these tools intelligently to explore physics that we can still get to explore. So we're having a lot of fun doing that. And so my final, big thought, if you will, is that this explainable machine learning can open doors for our field, I think, if we wield it carefully and intelligently. Okay, thank you.
Thank you, Libby, for that broad-reaching and really thought-provoking talk. I really enjoyed that. Well, thank you so much, Dr. Barnes. I know we're coming up to the cutoff, so I'll turn it back over to John for any closing messages.
No, I just want to say thank you again for a very stimulating talk. I really appreciate you taking the time to talk to us. I do wish that we could have had you here in Austin at some point in the future. We'll be able to have live presentations again, and hopefully we'll be able to have you out another time when we can do that in person. And thank you very much, and we'll see everybody next week.
Thank you.
Thank you.
Everybody.